Feeder protection is a broad term that refers to sub-transmission lines and distribution circuit protection. Sub-transmission lines refers to lower voltage transmission lines that connect the transmission system to the distribution system. Distribution circuits connect the sub-transmission system to the utilization apparatus. The issues surrounding sub-transmission and distribution system protection are very similar. In most cases, instantaneous and time-over-current protective elements, in addition to directional elements, are the most economical approach for both phase and ground fault protection. In this next section, we will take a look at the most common protective elements, which are the overcurrent elements. We will be studying their operating characteristic curves and how they are applied to the protection of distribution circuits. Modern microprocessor-based protective relays support many different protective elements. These elements may require one or two power system quantities, such as current or voltage. If only one measured quantity is used, the protective element will respond to the measured quantity over time. If the protective element uses two quantities, such as both current and voltage, the element may respond to the phase angle between the two quantities, the magnitudes of the two quantities, or to a combination of magnitude and phase angle. In protective relaying, it is common to use an operating characteristic to show the relationship between the quantities that will cause the relay to operate. As stated earlier, if only one measured quantity is used, the protective element will respond to the measured quantity over time. The operating characteristic will take the form of a graph with the measured power system quantity plotted on the x-axis against time on the y-axis. The graph, or operating characteristic curve, clearly demarcates the boundaries between three regions. The first is the none-operate region, and as the name implies, the element will not operate when the intersection of the two measured quantities falls within this area. The second is the curve which represents the point at which the element picks up. The third region is the operate region. The element will operate when the intersection of the two measured quantities falls within this area. Operating characteristic curves are useful for determining the relay settings that will provide the necessary speed, selectivity, and sensitivity to protect the power system and to coordinate with other protective devices. It is common for the curve to be drawn such that it does not extend to either axis. When the curve is drawn like this, it is implied that for every value of x beyond the curve, the value of y will remain the same. A very common requirement is to remove a component if the amount of current flowing into the component exceeds certain levels over certain amounts of time. The time and instantaneous overcurrent elements were created for this purpose. The instantaneous overcurrent protective element operates once the current has exceeded a pre-programmed level. If electromechanical relays are used, the relay will require some short time to operate. Where it is desired to have more time delay before operating, the time overcurrent protective element is used. The trip time varies inversely with current. The element will typically support several characteristic curves. The three characteristic curves most commonly used in North America are called inverse, very inverse, and extremely inverse. They are said to be a family of curves. In other parts of the world, different sets of curves are used, and some, like the multilin relays, allow you to create your own curves. During the selection of the curve, the protection engineer will be able to use a time multiplier to effectively shift the curve up or down on the time axis, in addition to a scaling adjustment to normalize the curve to the desired pickup level. That is to say that the pickup will be equivalent to 1 per unit or 100% on the x-axis. The setting of a series of coordinated time overcurrent relays on a feeder or distribution circuit begins at the point farthest removed from the generating source. As the relaying is set and coordinated back toward the generating sources, the time required to clear a fault becomes longer as the source is approached. Under certain fault conditions, this could be a disadvantage, and so instantaneous overcurrent elements are used in conjunction with the time overcurrent elements to provide high-speed primary protection. These elements must be set to pick up under maximum fault current conditions for three-phase faults somewhat short of the end of the line. The shaded area of the figure illustrates the improvement in tripping time obtained with instantaneous elements. Ground relaying of sub-transmission and distribution circuits is accomplished by means of instantaneous, time overcurrent, and directional overcurrent elements. These elements can generally be made to operate faster and with more sensitivity for ground faults and still maintain selectivity because their connections render them immune to load currents. The directional element requires a source of polarization that is obtained either from a current transformer in the neutral of a power or grounding transformer, or from the broken delta of a grounded neutral wide delta potential transformer bank. In many areas of the distribution system, fusing is the most economical form of overcurrent protection, and so they are used in many locations in conjunction with protective relays. There are many different types of fuses. If the feeder is to supply a large load, the equipment manufacturer will make fuse recommendations. The basic characteristics of fuses are as follows. They consist of one or more silver wire or ribbon elements called fusible elements suspended in an envelope. When high currents flow, the fusible element melts almost instantaneously, disconnecting the protected element. The time current characteristics of a fuse have two curves, the pre-arcing curve and the total clearing time. The pre-arcing curve is the time between the initiation of a current large enough to cause the fusible element to melt and the instant when arcing occurs, while the total clearing time is the total time elapsing from the beginning of an overcurrent to the final circuit interruption. The time current characteristic curve of a fuse follows an I²T characteristic. That is to say, as the current goes up, the time drops by the square of the current increase. When selecting a fuse, the criteria that is taken into consideration is as follows. The melting curves, the load carrying capabilities, the continuous current, which is defined as the maximum current expected for 3 hours without damage to the fuse, the fuse's hot load pickup, which is the maximum current that is carried continuously, then interrupted and immediately reapplied, which does not blow the fuse, cold load pickup, voltage rating, and interrupting rating. It is very important to coordinate the overcurrent protection. Take the example system shown. If a fault were to appear, the fuse F1 should open. If it were to fail, the feeder circuit breaker should trip a short time later because its protection has been properly coordinated with the downstream fusing. Properly coordinated protective devices help to eliminate service interruptions due to temporary faults, minimize the extent of faults in order to reduce the number of customers affected, and locate the fault, thereby minimizing the service outages. Our example system having one generator can be described as a radial system. The term radial system refers to a power system in which there is only one source of power. This aids in simplifying the process of applying protection. When applying protection, we normally perform a fault study starting at the generator and working to the load, and then a coordination study from the furthest load back to the generator to apply the protection. During the process of coordination, the operating characteristic curves of all overcurrent protective devices are plotted on a current versus time curve to ensure that no two curves cross over and there is adequate distance, or more correctly, time between curves or discrimination between curves. The discrimination ensures that the device closest to the fault operates first, taking into account such things as timing errors, overshoot time, circuit breaker opening time, and safety margins. The operating time of a fuse is a function of the pre-arcing or melting and arcing time, and follows the I²T law as stated earlier. For proper coordination, total I²T of the secondary fuse shouldn't exceed the pre-arcing of the primary fuse. This is established if the current ratio of the primary versus the secondary fuse current rating is 2 or greater for fuses of the same type. It is important to note that the relay should back the fuse up over full current range, and that no characteristic crossing occurs. The relay characteristic curve best suited for coordination with fuses is the extremely inverse, which is similar to the I²T fuse curves. For extremely inverse relay curves, the primary pickup current setting should be 3 times fuse rating. For other relay curves, up to 4 times fuse rating should be considered, therefore ensuring that there is no crossover between the relay and the fuse curve. To account for CT saturation and errors, relay overshoot, timing errors, and fuse errors, a minimum discrimination time of 0.4 seconds should be considered. A sectionalizer cannot interrupt fault current, but works as follows. It counts the number of times it sees fault current and opens after a preset number while the circuit is de-energized. Reclosers, on the other hand, have limited fault interrupting capability. If a fault is seen that the recloser can handle, it will open and then reclose automatically in a programmed sequence. The instantaneous and time overcurrent elements, which are device numbers 50 and 51 respectively, are the most common overcurrent elements applied in this type of application to meet the needs of the protective scheme. The instantaneous overcurrent protection element is set to a value that is less than the maximum fault current calculated in the short circuit study, but higher than the pickup of the relay's time overcurrent element. The selection of the overcurrent protection curve is based on time grading of the relay operating characteristics. To illustrate proper coordination between the sectionalizer, recloser, and fuses, we will now describe how the system should respond to faults at different locations. For a fault at location F1, the sectionalizer cannot interrupt fault current, therefore the recloser clears the fault. If the sectionalizer is set to 1, it will disconnect the line once the recloser clears the fault, allowing the recloser to close to ensure service to the unfaulted section. If the sectionalizer is set to 2, the sectionalizer will not open after the first trip. It allows the recloser to reclose for a second time. For a fault at location F3, the recloser trips and recloses according to its setting. For a fault at F2, the fuse clears the fault first. If it fails, the recloser clears the fault. Fault current and interrupting requirements increase with voltage. Therefore, protection shifts from a fuse or recloser over to relays and circuit breakers. Coordination of the devices on a distribution system means they are timed to operate one after the other in a particular sequence. The timing of operation is determined by curves plotted on a time over current graph. These curves are calculated through an in-depth phase over current analysis of the distribution system. There is some distance between each device curve because we require a delay in operation between each device. This distance is known as discrimination time. Auto-reclosing. Around 90% of the faults on overhead lines are transient in nature. The remaining 10% faults are either semi-permanent or permanent in nature. Tripping of one or more circuit breakers will normally clear a transient fault, and reclosing of the circuit breaker will re-energize the line and restore supply to the consumers. When a fault occurs on a power line, the protection element of a modern protective relay will detect the fault and issue a trip command to the circuit breaker. At the same time, the auto-reclose cycle is initiated. After a predetermined time, known as dead time, the closing command to the breaker is issued. If the fault was transient in nature, then the breaker will remain closed and the supply will be restored. However, if the fault was permanent in nature, then the relay will re-trip the circuit breaker. The main advantages of the auto-recloser are improved energy supply to the consumers with less interruption time, and reduction of substation visits with reduced maintenance cost. SynchroCheck. Let's look at the following example to explain the SynchroCheck. The transmission line is connecting two substations. The circuit breakers at A and B will trip in case of a line fault. Once the circuit breakers are open for a set period of time, there is a possibility that the following system parameters may drift apart from acceptable level: the phase angle of the systems, voltage, and frequency. If that happens, the system is said to have lost synchronism. If we reclose the breakers under such situations, serious damage could occur. It is usual practice to incorporate a synchronism check relay, or SynchroCheck function in a multifunction relay, into the reclosing system to determine whether auto-reclosing should take place. Usually a circuit breaker at one end will be closed first. Before closing the other circuit breaker, the SynchroCheck relay or SynchroCheck element will check if the phase difference, voltage difference, and frequency difference between two parts of the power system is within acceptable limits. If so, reclosing of the second breaker will be initiated. The differential element introduction. The current differential element is the primary protective element used for bus, transformer, motor, generator, and line protection. This section of the course will focus on bus and transformer specifically. A differential element is one that operates when the vector difference of two or more similar electrical quantities exceeds a predetermined amount. Therefore, the current differential element looks at the difference between the current entering and the current leaving the zone of protection. If the difference exceeds a given amount, the element will operate. The simplest example of current differential is the arrangement shown here. The system component being protected might be a bus or a portion of a bus, a transformer, windings of a motor or generator, or a section of a transmission line. Current transformers are positioned on either side of the system element, forming the boundaries of the zone of protection. Under normal operating conditions, the secondary currents of the CTs are summed after any required scaling and phase angle correction, as would be the case for transformer protection. If the difference is within an accepted range, which can be attributed to CT error, the element will not operate. If the protected device develops a fault which results in a difference greater than an acceptable amount, the elements will operate. Percent differential example. Let's substitute some figures to better understand the operation of the differential element. On an example circuit with a maximum load current of 100 amps using standard protection class CTs with an accuracy of 10%, a maximum error of no more than 10 amps per CT is expected after summation. This would lead to a maximum cumulative error of 20% or 20 amps. However, if the element were set up to simply operate once the difference was greater than 20 amps as opposed to 20%, it was found that the element wouldn't work correctly under certain conditions, the most common being a through-fault condition with large fault currents. A through-fault condition is when a fault develops at a point beyond the zone of protection, such that a large amount of current flows through the zone. For example, let's say the fault current was 1,000 amps. I1's secondary current might correspond to 1,050 amps, while I2's might correspond to only 950 amps. Note that both CTs are well within their specified 10% accuracy. However, the 100 amp difference would be greater than the 20 amp maximum fixed difference, so the element would operate for this out-of-zone fault, which isn't desirable. The solution is to create an operating characteristic that is very sensitive to differences at low current levels, yet secure at higher current levels. The most common solution is to use what is called a percent differential characteristic. This characteristic is plotted on an XY graph as follows. The absolute difference between the two currents is plotted on the y-axis, ID, while what is referred to as a restraining current, labeled IR, is plotted on the x-axis. There are several accepted methods for calculating the restraining current. These methods are known as the sum of, the scaled sum of, the geometric average of, and the maximum of. Each of these methods is used by various vendors on various differential relays. There is no significant advantage of using any particular method over another. The amount of restraint provided by various methods is different, sometimes significantly, particularly in the case of multi-circuit differential elements such as is the case of busbar protection. Before the percent differential is calculated, the maximum error of the CTs must be plotted on the graph and is displayed in the form of a slope. For example, if each CT has a maximum rating of 10% error, then the maximum error is plotted as 20% in the form of a linear slope. Any reading plotted above the slope is in the operate region, which will cause the element to operate. Anything below the slope is in the non-operate region, not requiring the element to operate. The percent differential is then calculated using the following formula. The absolute value of I1 minus I2 divided by the restraining current times 100%. I1 and I2 are read through the use of the CTs, but the restraining current must be determined using one of the methods previously discussed. In our example of an external fault, the maximum measured current is 1,000 amps, and so using the maximum of method for determining restraining current, we will set the restraining current to 1,000 amps. The absolute difference between I1 and I2 is calculated by the element to be 100 amps. The percent difference is then equal to 100 amps divided by 1,000 amps times 100%, equaling 10%. Since the slope was set to 20%, the element will not falsely trip under the through-fault condition. CT saturation. Bus and transformer fault currents tend to be very large, and so we must be concerned with the possibility of CT saturation. Earlier in this course, we discussed how CTs would work linearly up to a maximum current, the knee point. Beyond the knee point, their current readings will no longer be accurate. CTs used in a differential application are never perfectly matched, and so during a fault, one of the CTs will saturate before the other. Once one of the CTs starts to saturate, an additional spurious differential current will be measured by the relay. Note that even when a fault occurred that results in deep CT saturation, the CT would initially step down the current correctly. The operating point's initial trajectory will be such that it departs from the pre-fault point position and will shift to the right, as was the case in the previous example. Once the CTs go into saturation, the measured current, and therefore the restraining signal, decreases. This causes the operating point to shift trajectory up and to the left. With enough saturation, the operating point could enter the element's operating region, resulting in a maloperation. To provide greater security under large through-fault current conditions, the element uses a steeper slope beyond a pre-programmed breakpoint. The resulting shape is called a dual-slope percent differential characteristic. The slopes and breakpoint for the dual-slope percent differential characteristic are calculated as follows. The breakpoint. If using the maximum of method for the restraining current calculation, the breakpoint or transition point between slope 1 and slope 2 is normally set to a current just above the maximum overload load current of the device being protected. Slope 1. The normal maximum setting of slope 1 is the cumulative rated error of the CTs. For example, if both CTs have a 10% accuracy, the slope would be set to 20%. Having said this, if the maximum fault current will generate a voltage that is less than or equal to half the knee point voltage of the CTs, it is common practice to reduce the CT's rated error by half. Therefore, the CT rated accuracy of 10% would be reduced to 5%, and the slope recalculated to be 10%. This provides greater sensitivity for low-level faults. Slope 2. Using the maximum fault current from the fault study, the maximum CT saturation is then determined by testing the CTs. The second slope is then plotted such that the element will not operate under worst-case calculated CT saturation conditions. The operating region boundary is now formed by slope 1, the breakpoint boundary, and slope 2 as illustrated. System error. Under normal operating conditions, it was found that the element could maloperate under extremely light load conditions due to system error. System error is the cumulative error of the CTs and the analog-to-digital converters within the relay. The total of this error is typically very close to the rated CT error. To eliminate the possibility of maloperation under such conditions, the element has a setting for the minimum differential error to cause operation. The system error would be determined by accurately measuring the difference between the actual current and the current displayed by the relay. The actual difference is called the system error. This value would then be entered into the element, resulting in the final operating characteristic appearing as shown. Currents below this level will block the element. One of the most common applications of differential protection is the protection of a bus. Protection of power system bus bars is one of the most critical relaying applications. When a fault occurs within the busbar areas of a power system, fault current levels may be very high. In spite of this, some of the circuits connected to the bus may have their current transformers insufficiently rated. This creates a danger of significant CT saturation and jeopardizes security of the busbar protection system. A false trip of a distribution bus can cause outages to a large number of customers, as numerous feeders as well as sub-transmission lines may be disconnected. A false trip of a transmission busbar may drastically change system topology and jeopardize power system stability. Hence, one of the requirements of busbar protection is a high degree of security. On the other hand, bus faults generate large fault currents. If not cleared promptly, they endanger the entire substation due to both dynamic forces and thermal effects. As a result, the second requirement of bus protection is that of high-speed operation. With both security and dependability being very important for busbar protection, the preference is always given to security. Bus protection. Power system busbars vary significantly in terms of their size, meaning the number of circuits connected, complexity, number of sections, tie breakers, disconnectors, voltage levels, transmission levels, and distribution levels. In the past, these technical aspects combined with economic factors led to a number of solutions for busbar protection. The most common schemes are high impedance, linear couplers, interlocking, overcurrent or unrestrained differential, percent differential, and finally low impedance microprocessor based. Let's take a look at the operation of each. High impedance. The scheme requires only a simple voltage level sensor. From this perspective, the high impedance protection scheme is not a relay. If breaker failure protective elements, event recording, oscillography, communications, and other benefits of microprocessor-based relaying are of interest, then extra equipment is required, such as a digital fault recorder or dedicated breaker failure relays. Linear couplers. A linear coupler, or air-core mutual reactor, produces an output voltage proportional to the derivative of the input current. Because they are using air cores, linear couplers do not saturate. During internal faults, the sum of the busbar currents, and thus their derivatives, is zero. Based on this, a simple busbar protection scheme is achieved by connecting the secondary windings of the linear couplers in series in order to respond to the sum of the primary currents, and connecting a simple voltage sensor to either end. The disadvantages of this approach are similar to those of the high impedance scheme, in addition to the fact that linear coupler schemes are not as common. The interlocking scheme. A simple protection scheme suitable for distribution busbars can be accomplished using an interlocking scheme. The interlocking scheme consists of overcurrent relays that are placed on the incoming circuit and at all outgoing feeders. When a fault occurs on this outgoing feeder, the overcurrent relay on the incoming circuit will send a trip signal into the on delay. This delay is present so that the feeder overcurrent relay associated with the fault will have a chance to operate and also send the blocking signal to the incoming circuit overcurrent relay, therefore blocking its operation. This prevents the rest of the system from being unnecessarily shut down. When using microprocessor-based multifunctional relays, it becomes possible to integrate all the required OC functions in one or very few relays, thus not only reducing wiring and coordination time, but also speeding up the operation of the scheme. Modern microprocessor relays, which have a fast peer-to-peer communication service, such as the UCA Goose messaging mechanism, can be used to send the blocking signal, eliminating the relay-to-relay hardwiring required for the block signal. The scheme, although easy to apply and economical, is limited to specific simple busbar configurations. Overcurrent differential. Typically, a differential current is created externally to a current sensor by summation of all the circuit currents. Preferably, the CTs should be of the same ratio. If they are not, a matching CT or several CTs is needed. This in turn may increase the burden for the main CTs and make the saturation problem even more serious. Historically, means to deal with the CT saturation problem include definite time or inverse time overcurrent characteristics. Although economical and applicable to distribution busbars, this solution does not match performance of more advanced schemes and should not be applied to transmission-level busbars. The principle, however, is used as a protection function in an integrated microprocessor-based busbar relay. If this is the case, such unrestrained differential elements should be set above the maximum spurious differential current and may give a chance to speed up operation on heavy internal faults as compared to a percent or restrained bus differential element. Percent differential. Percent differential relays create a restraining signal in addition to the differential signal and apply the percent or restrained characteristic discussed earlier. The difference ID is the resultant of the vector sum of all currents feeding the bus, while the choices of the restraining signal include sum, average, and maximum of the bus currents. Typically, manufacturers will choose either the single or dual slope characteristic. This low impedance approach does not require dedicated CTs, can tolerate substantial CT saturation, and provides high-speed tripping. This principle became really attractive with the advent of microprocessor-based relays because of the following. Advanced algorithms supplement the percent differential protection function, making the relay very secure. The relay can perform CT ratio compensation, eliminating the need for matching CTs. Protection of a bus that can dynamically change its configuration can be accomplished without switching secondary current circuits. Integrated breaker-fail function can provide optimal tripping strategy, depending on the actual configuration of a busbar. And distributed architectures are proposed that place data acquisition units in bays and replace current wires by fiber optic communications. Transformers consist of a primary set of windings and one or more sets of secondary windings used to isolate, phase shift, and/or step the voltage up or down. Depending on the transformer, the primary and secondary windings can be delta, Y, or zigzag configuration. This is an example of a two-winding delta-Y three-phase transformer. Transformers are given an apparent power rating based upon the transformer's voltage and current limits. This VA rating is the same for both the primary and the secondary windings. Given the primary and secondary winding power rating is the same, the current in the secondary will be inversely proportional to the current in the primary, or turns ratio. The ratio of the primary to secondary voltage is determined by the turns ratio of the primary to secondary windings. The turns ratio represents the ratio of turns in the primary coil to the turns in the secondary coil. Each coil is wrapped around an iron core to improve the efficiency. The number of turns refers to the number of times the conductor is wrapped around the core. In order for the voltage to be stepped up or down, the number of turns in the primary and secondary coils will not be equal. For example, if the primary winding has half the number of turns as the secondary, the primary will induce twice its rated voltage into the secondary, meaning the voltage is being stepped up. The maximum amount of current available on the secondary will be reduced such that the overall power rating of the secondary will match the primary. If the number of turns on the secondary winding were less than that of primary, the voltage would be reduced and the available current would increase inversely proportional to the voltage reduction, such that the secondary power rating would match the primary. The relationship between the turns ratio, voltage, and current can be expressed with the following formulas. Transformers are rated by their primary and secondary voltage relationship and their power carrying limits. For example, a typical substation transformer might be rated 138 to 25 kilovolts and 10 megavolt amps, meaning the primary or maximum voltage rating is 138,000 volts. The secondary or low voltage rating is 25,000 volts, and the transformer has a power rating of 10 megavolt amps or 10,000 kilovolt amps. A study performed on transformer failures found the following information. 51% were classified as winding failures, which include turn-to-turn failures, surges due to lightning, moisture, external faults, overheating, open winding, or deterioration. 19% were related to a mechanical failure of the tap changer. 9% were attributed to bushing failures due to aging, contamination, or cracking. 6% can be traced to loose connections on the terminal board. 2% were due to core insulation failures. And the remaining 13% were simply classified as miscellaneous failures. The percent differential protection element, which is considered the primary protective element for transformer protection, can detect most of these failures. Differential protection. As stated, the primary protective element for the transformers is the percent differential element, which compares the current entering and leaving the transformer. Modern microprocessor-based transformer percent differential relays, such as the GE Multilin T35, T60, and SR745 relays, have built-in compensation for the turns ratio and phase shift, and so neither of these topics will be addressed. For further information on the percent differential element's theory of operation, please reference the percent differential section of this course. When applying differential protection to a transformer, there are several factors that must be taken into consideration, which are magnetizing inrush or second harmonic, fifth harmonic current, voltage per hertz, arc detection, and sudden pressure. We will now examine each of these issues. Magnetizing inrush or second harmonic. This is a normal characteristic of a transformer that is being energized. When the system voltage is applied to a transformer at a time when the steady-state flux should be at a different level from that existing in the transformer, a current transient, known as inrush, occurs to build up the flux. Inrush currents between 8 to 30 times the full load current flows into the transformer with no current flow out. This current flow would normally appear as an internal transformer fault to the differential element. However, many years ago it was determined that there is a large second harmonic component of this inrush current. Modern microprocessor relays include a harmonic restraint feature to assure that the relay will never operate on inrush. Let's take a closer look at harmonic current restraint. The principle of harmonic current restraint makes a differential relay self-desensitizing during the magnetizing current inrush period, but the relay is not desensitized if a short circuit should occur in the transformer during the magnetizing inrush period. The relay is able to distinguish between magnetizing inrush current and short circuit current by the difference in wave shape. Magnetizing inrush current is characterized by large harmonic components that are not noticeably present in short circuit current. A harmonic analysis of a typical magnetizing inrush current wave was as shown in the accompanying table. Fifth harmonic current. Transformers that are connected directly to a generator that is brought into or removed from service or the failure of an upstream tap changer may result in an overvoltage condition. If the applied voltage rises above the rating of the transformer, known as overexcitation, a fifth harmonic current is generated. Depending on the amount of overexcitation, this fifth harmonic current could rise to a level that could cause the main differential element to operate. Short-term overexcitation is a common occurrence on a power system and is especially true for transformers connected directly to generators, and so this element is used to restrain or block the main differential element from operating when fifth harmonic currents that are present are large enough to cause the main differential element to operate. Voltage per Hertz protection. Transformers must not be subjected to prolonged overvoltages. For maximum efficiency, they are operated near the knee of the iron saturation curve, such that slight overvoltage results in significant exciting currents in the transformer. The voltage per Hertz element is set up as a backup to the generator control system and the differential element when blocked by the fifth harmonic restraint feature just discussed. It is recommended that 2 voltage per Hertz elements be set up, one at approximately 110% to generate an alarm and trip in about a minute, while the second is set to approximately 120% with a trip time around 6 seconds. Arc detection. When a high or low-level fault occurs within the transformer, usually an arc forms. This arc causes the oil within the transformer to break down and gas is formed. The speed at which the gas is formed is proportional to the size of the arc and hence the fault. The transformer design determines how this gas is detected. In European transformer design, there is no space for the gas to collect, so a conservator tank is connected to the transformer. A gas accumulator device, known as a Buchholz relay, is connected between the transformer and the conservator tank or tanks. If a low-level fault results in arcing, the small amount of gas that is produced will accumulate in this relay, which will then issue an alarm. If there is a sudden large increase in the amount of gas being produced corresponding to a large fault, the relay will sense this and trip the transformer offline. Sudden pressure. In North America, oil-immersed transformers will have sudden pressure sensors. One style will operate on a sudden change in the oil, while the other operates on a sudden change in the gas above the oil. They have inverse time characteristics, meaning they will operate very quickly for a high-energy arc and trip the transformer offline, while they will operate slower for a lower-energy arc and may at first only issue an alarm.